Okay, so I want to continue working on the coupled wave analysis, and we're going to develop, again, a way of solving for what the efficiency will be for a grating that has some thickness to it, in a sense that we have many interactions of the light with the scattering planes as it passes through. So again, if we have our grating looking something like that with, again, a period and a grating vector which is perpendicular to the fringe planes at some angle phi to the z-axis. Here's our x-axis, and we come in here with a wave. We're calling this the signal, or I'm sorry, the reconstruction wave here with a propagation constant rho. We will then figure out what the overall diffracted field is going to be coming out of this system. And so, again, we have some thickness d, and we're assuming, again, that this grating, one of our assumptions was that we don't have any real hard boundaries. So that is going to buy us some things in the way of simplification in the analysis of this grating. So the way that we'll solve it is again to solve the scalar wave equation, or the Helmholtz equation, and we have kind of tucked away in this k squared term, this propagation constant squared, the modulation term. So we have a average modulation plus some amplitude of that cosine of k dot r, where k is this coupling is the grating equation, and we can also have again modulation of the conductivity, which is going to give rise to a absorption grating effect, which will appear to some degree in almost all gratings. Ideally, so again, this is going to give us a phase grating, and this is going to give us an absorption modulated grating. Ideally, we'd like to go for this phase grating, because if we have absorption, even as we saw in the thin grating case, we are greatly going to reduce the overall efficiency that we can get, because some of that light's being absorbed. Whereas in the case of the phase grating, we can potentially transfer all of the light into a diffracted order where we want it to go. All right, and so here again, so we have this again using, for instance, an average propagation constant beta squared 2 pi n over lambda, and an average absorption. We end up with this propagation constant k squared is equal to beta squared minus 2j alpha, the average absorption, beta, plus 2 times a coupling coefficient, kappa, beta, e to the j k dot r, plus e to the minus j k dot r. And this kappa is the thing that differentiates this kind of solution to the wave equation from kind of an average medium propagation characteristic. Here we have the average phase, here we have average absorption, but here we have, this is the modulation as represented by this k vector that we see tucked away in there, and the coupling coefficient that we have, this kappa, in optical media, meaning that we don't have too much absorption. We have a significant degree of propagation in the medium, so we have, say, this average propagation constant is much greater than the absorption that we have. In that case, we can write kappa in a simplified form that we'll use mostly pi n1 over lambda for the phase modulation, this permittivity modulation, minus j alpha 1 over 2. All right, so again, this coupling coefficient, when it's there, we're going to have some interaction with the grading. Okay, now one reason this is important, this grading vector appearing in that phase term for the propagation constant, is that this is going to relate our two fields. We have this R field, and then we're going to have some signal or diffracted field coming off at some signal direction with the propagation constant sigma. And so with that coupling coefficient, the other important feature is that we have the Bragg condition. So these two factors are the two parameters that are really going to give us the overall grading performance in our system. And we also, along with this vector relation, last time we derived the scalar form. So this is the Bragg condition for the grading, and we came up with the scalar form for that, which is cosine of phi minus theta equals k over 2 beta. All right, so when in fact theta corresponds to, say, an angle which would have been used in actually forming those fringes during the construction phase of the hologram, we will have the Bragg match condition, so we can designate that as phi 0 for the Bragg angle. And also notice here, so this is the magnitude of k, and beta is 2 pi n over lambda. So this also corresponds to a Bragg wavelength, right? So we have also a Bragg wavelength here, 2n times the period. So when we have, the right set of conditions for the reconstruction, meaning the Bragg condition, we will have very high diffraction efficiency for this grading. Okay, so those were some of the things that we discussed. We also mentioned that, so what if we're not at the Bragg condition, okay, which is often the case, and we want to have some off-Bragg performance for gradings. So for that, we have this parameter, we can call it the detuning parameter. Detuning, in the sense, this is away from the Bragg condition, okay? And that's what we mean by detuning. And that detuning parameter, we'll define it as the difference between the average propagation constant for the medium squared minus the propagation constant for the diffracted field squared, and normalize that to this average propagation constant, okay? So, so that is a detuning parameter, and again, the notion of that can be indicated through the Bragg circle. Okay, very, again, nice, convenient graphical description of kind of this Bragg characteristic. So here, if we have, again, the Bragg condition where we have, rho and sigma here, and again, this radius in this case is equal to beta if we're at the Bragg condition. And this is our k vector, right? So if we then decide, well, we want to reconstruct it at a different, say, angle here, so we're now going to go to rho prime, we have the same grading vector, and we see now that we can no longer get a signal beam which is going to lie on this circle. And so, we're in a bit of a difficulty there in the sense that we are no longer Bragg matched. So this difference is really what we're talking about in terms of this detuning parameter. this is the meaning of the detuning. Okay, how far away from the Bragg condition are we? And as we'll see, that's going to impact the overall efficiency that we have. So we can also, we don't want to go too far from the Bragg condition, so we can actually then simplify this detuning parameter to some degree. This in its full form is equal to k cosine of phi minus theta minus k squared over 4 pi n lambda, all right? So if we are close to the Bragg condition, which most of the time we're going to have to be. For some materials, again, we have, an angular bandwidth that's only, it's like 0.02 degrees, and we're trying to get it even smaller than that for a very selective application. So there's many times when this is the case. So we can make some simplification. So let's say that we have theta now is equal to theta 0 plus delta theta, and lambda equals lambda 0 plus delta lambda. All right, and so when we have that being close to the Bragg condition, we can simplify this relation for the detuning parameter now to k times delta theta sine of phi minus the Bragg angle. Okay, so that's the Bragg angle. And minus delta lambda over 2n times the period. Okay. So this is useful because we can see, how, let's say if we, like I think in the homework, yeah.
What symbol are you using for the detuning parameter? Sorry, just for my note-taking purposes, I feel like I'm drawing a 9.
This is the best I could figure it is the Greek symbol for J. If you type in J in a symbolic text, I ended up with that symbol. So I figured that was the Greek symbol for J. So that bothered me for a number of years, by the way, and I finally did a little research by playing around. I still don't know if that's true or not, but I think that was the best answer I have for you right now. It's not 9, but it is J. Okay, so I think in the homework problems, I ask you to, and also problems I like to ask on tests are things like, okay, so if you have a certain amount of angular detuning, what is the equivalent wavelength detuning? Okay, so this function here is very useful for that, right? Because you can just set these two equal to one another and see how much of wavelength detuning corresponds to like 0.2 degrees of angular detuning or vice versa. So again, very useful to see this kind of duality. And as I mentioned a couple of times, this is really important experimentally because usually a rotation stage is much cheaper than a tunable laser, okay, so, or a monochromator. So, this is a nice way you can get the same information simply by going through and looking at this parameter and multiplying it out. Okay, so it has some really practical importance. Okay. All right, and again, so this detuning parameter too is very important because it's going to tell us the characteristics of the efficiency curve. All right, so if we're plotting here the diffraction efficiency, and here we have either theta 0 or lambda 0, this delta theta delta lambda is giving you, the full width half max of that efficiency curve. All right, and so this indicates all of this now is indicating the selectivity of the grading. Because if you detune too far, right, you're going to be out here, and you're going to have no efficiency for that grading. All right, and so this ties in a little bit too with we talked about the dispersion relation, and we mentioned that for the if we have a thin grading, right, we can use the grading equation sine theta 1 minus sine theta 2 equals lambda over the period for that, and we end up with a dispersion relation d theta d lambda that's equal to 1 over cosine of, say, theta d, the diffraction angle, or one of these angles that we have, times the period, all right? Whereas for the volume grading, the way we got that was we differentiated the Bragg condition here, all right? And so for the volume grading, we end up with a different relation for that. So here we have that d theta d lambda is k, the magnitude of the grading vector, over 4 pi n sine of phi minus theta. All right, so it's somewhat different in a sense, and we can simplify that a little further, and this works out to be 1 over 2n period sine of phi minus theta. And this is maybe a better way of showing it, because we notice that both of these dispersion relations, again, are related to the inverse of the period. So the finer the period, the more dispersion. Now, there's kind of a very subtle difference, though, between the dispersion for the thin grading and that for the volume grading. For the thin grading, what we mean there is that if we have, again, we have our set of point scatterers here, and we come in at some theta incident here with lambda 1, lambda 2, we'll end up with, a different angle due to the phase matching. All right, so here this may be for lambda 1, and this may be for lambda 2. And so we have a theta d here, and we have a theta d prime. So the thin grading dispersion is a function of the phase matching, which is what is being, again, described by the grading equation. So these are kind of subtle points, but they're important subtleties. For the volume grading, what we're really talking about here is the Bragg condition, right? That's how we derived it. And what does that Bragg condition represent? Well, here we have k, the grading vector, and for instance, we have one set of matching propagation vectors here at k1 and k2 with, say, theta 1 for the angles. Let's say that they're equal, and this is a unslanted grading. The dispersion relation for the volume grading, though, represents the other Bragg match conditions that we can have for this grading. So this is, say, k1 prime and k2 prime. Okay, so you see that we could still have Bragg matching, starting out from when we have kind of the longest wavelength that we can match is indicated here, and then we could match at other wavelengths. So I have a nice picture of this actually for a volume grading. I'm finishing up a thing for SPIE, and I'll share it with you later, but you get very nice high efficiency dispersion as wavelengths and power. So you can see here that we're always getting Bragg matching. So that means we can get high efficiency, right? But to achieve that high efficiency, we have to be at a different angle, okay, to do that. So what does that mean? So that means that if we come in here with a beam with multiple wavelengths, lambda 1 and lambda 2, we're going to see one beam will be dispersed here for, say, lambda 1, and lambda 2 is going to be dispersed here. So we, for instance, we're making a lot of these solar useful elements, holographic elements for solar applications. And one of them is to kind of disperse the sunlight and then use solar cells with different responsivities matched to where spatially these wavelengths are distributed. All right, so this is the meaning for dispersion in the volume grading sense. So this one relates to the Bragg condition, which again is representative of the diffraction efficiency. And the thin grading is described by the grading equation. And that is a phase matching condition. Okay, so it's a subtle difference. The equations are not too different, right? But it has a very different meaning, okay, in both of those cases. All right. Okay, so that was again, that was kind of a synopsis of what we talked about, and I thought it was worth spending a little time going over, because if you don't understand what I just went through, you're not going to understand the rest of this. So it's kind of the core features of the coupled wave analysis. So if you kind of go through that again, if you have questions, bring them up later or next time. Let's really go through that, because I think with an understanding of that, we'll be able to really have a good knowledge of the coupled wave theory and analysis. Okay, so now let's look at the solution. And there was, okay, so there's a couple of things that we're going to do in this solution. First is, again, we'll use the Helmholtz equation, which is del squared E plus k squared E equaling 0. We have, the other thing we have at our disposal is k squared, right? And so k squared is, again, equal to beta squared minus 2j alpha beta plus 2 kappa beta times e to the j k dot r plus e to the minus j k dot r. Okay, so that's another thing that we have. And then the next step here, or the next component of our solution, is going to rely on the fact that the field, remember we mentioned this is one of our assumptions, that the field that we have is only a function of x and z. We assume it's kind of the same in the y direction. And this has only two components. It has the reconstruction source, which, again, the amplitude of that reconstruction source is only a function of the depth of penetration into the medium, times the phase term, e to the minus j rho dot r, where rho is the propagation constant, plus a signal beam, s of z, e to the minus j sigma dot r. Okay? So that is another element of our solution. And the final component that we're going to take advantage of and utilize is the Bragg condition. Okay, and so that is, again, sigma equals rho minus k. All right, so what we have to do now is put all these things together and come up with a solution. All right, so First off, or just kind of refresher here. So del squared, this is the set of second derivative partials in the x, y, and z directions. We have r, right? What is r? The vector r. That's equal to x plus y plus z. And we have sigma. We can write this as sigma x plus sigma y plus sigma z, and rho equals rho x, plus rho y plus rho z. So it's always good to kind of lay these things out so we can see how they come together when we get into the nitty-gritty. All right, so here's our equation that we have to solve, right? So we have two parts, so let's take the first part. So we want to come up with del squared E, that part of it, all right? And so we need to have, take the second derivatives, but before you take the second, you have to take the first, right? So we have rho with respect to x, and so that's equal to, we have a minus j rho sub x r e to the minus j rho dot r, right? And we have same for the s field, because that's our e, right? So we're doing that one, then that one, minus j sigma xs e to the minus j sigma dot r. Okay, and then for the y, of course, it's the same, so we don't have to write that out, but it's just substitute rho y and sigma y. And then we have the z part. Okay, the z is different because we have r is a function of z and s is a function of z. Before, these are not functions of x or y, so they just kind of fall out. We only had to differentiate the phase term. But here we have to, do kind of partial derivatives. So here we have minus j rho sub z r e to the minus j rho dot r plus, now we take so that was the same as here. Now we have to differentiate the amplitude. So we have r prime e to the minus j rho dot r. Then we have, for the s part, we have minus j sigma zs e to the minus j sigma dot r. And then we have differentiating the amplitude plus s prime e to the minus j sigma dot r. So this is the derivative with respect to z, is what I mean by that prime. Okay, so now we have the first derivatives, and so now we can get the second derivative. So we have second derivative. Now we differentiate that, and so here we end up with minus rho x squared r e to the minus j rho dot r minus sigma x squared s e to the minus j sigma dot r. And then we have, again, the same thing for y squared, just with a rho y and a rho, sigma y. And then now for the z, so we even have more trouble there because now we have to, we're going to multiply that by 2 in the number of terms that we're going to get in doing that. Okay, so here we end up with minus rho z squared r e to the minus j rho dot r minus j rho z r prime e to the minus j rho dot r plus r double prime e to the minus j rho dot r minus j rho z r prime e to the minus j rho dot r. Okay, so that's this part. Now we have that part for the s's. So kind of similar, minus sigma z squared s e to the minus j sigma dot r minus j sigma z s prime e to the minus j sigma dot r plus s double prime e to the minus j sigma dot r minus j sigma z s prime e to the minus j sigma dot r. Okay, you're going to like this. It just falls out really, really nicely in the end. But it's worth going through once at least to see where all these terms originate and then how it kind of collapses down to a nice set of coupled wave equations. Okay, so solving our Helmholtz equation, we got the del squared E. So now we have to do the k squared E, right? So let's do that part and then combine it and then see what we end up with. All right, so now we have, again, k squared E. All right, so again, that was, that's this thing here, so we have to get all that together. All right, and so we have, so this is going to be equal to beta squared E minus j alpha beta E. So again, this is just the average propagation terms. And then we have kind of the interesting stuff here. So now we have plus 2 times kappa beta times r. And then, so again, let's go up here and look at that. All right, so we have putting in, again, so we multiply by e by all that. But here in this term, we're going to expand e to be equal to that. So here we have r e to the minus j rho dot r minus k dot r, right? Because these phase terms now are going to combine up. And then we have plus s e to the minus j sigma dot k, that dotted with r. And then we have plus r e to the minus j rho plus k dot r, and plus s e to the minus j sigma plus k dot r. Okay, so we have all the parts now, but before we combine them, let's think about our assumptions for this analysis that we've made. Right? One of the assumptions was that we have sigma is equal to rho minus k. And the other thing was that we only have 2 waves, right? So we only have E is, so we have 2 components of E. We only have R and S, all right? And that's it. So I'm suggesting now that we can actually throw away half of these terms that we have here. So which ones should we keep and which ones should we eliminate? Which ones should we keep? Let me ask that. Okay. Well, this one obviously, right? This is rho minus k dotted with r, right? So this is going to be sigma, all right? And this one too, right? Because this one we could bring k over here and that's equal to rho. So this is going to be equal to rho. These 2 other ones go off in other directions, not rho, not sigma. And so these we can eliminate, okay? Right? Because that's part of what we said. We're only going to have 2 waves. We're not going to have any other coupled orders. These are going to give different diffraction orders, which we're not going to deal with. We're only talking about one signal wave, one diffracted wave in the system. Okay? So let's remind ourselves of something simple before we combine these. So here is the things.
Professor, quick question. Why did we get to choose which two waves we kept?
Pardon me?
Why do we get to choose which to keep only two waves? Is that better?
Well, because rho plus k is a different diffraction order, right? So if we have rho plus k, that's like a -1 order, all right? This is a +1 order, okay? And similarly here, if we have sigma plus k, that's not equal to rho, it's equal to like something else, right? Sigma plus k is going to be, well, that's this one we're keeping. Rho plus k, we're not.
Those two make more convenient sense, but I'm wondering why we're allowed to eliminate those other two.
Well, because what we said was that in this grading that we have, we're only going to say that there exist two waves, R
So we're just choosing which two we're going to work with?
and S, right. There could be some other diffraction orders going off at different, like these other two may correspond to some other diffraction orders like that. But we're going to say, we're not really going to treat those, okay, because it's going to make the math too complex for us, okay. So in the rigorous analysis, we keep those, okay, and we keep many more actually because we allow for many more couplings to occur and many more field terms. But in this analysis, that's why it's an approximate analysis. We're only going to keep these two orders that correspond to the Bragg condition, or these two terms. Yeah. Okay. Yeah. Thanks for asking. All right. So the magnitude of rho. So we're going to take advantage of this is rho x squared plus rho y squared plus rho z squared. And this is going to be equal to beta squared, and that's also equal to sigma squared, sigma x squared plus sigma y squared plus sigma z squared. Now, the reason I'm bringing that up is because we have sigma z here, for instance, in a couple of these different, and rho sub x's and sigma sub x squares and things of that sort. So we can kind of combine all those terms in the end, all right? So let's go ahead and do that. When we combine everything, we end up with the following two equations. We have r double prime minus 2j rho prime, rho sub z, minus 2j alpha beta r, plus 2 kappa beta s is equal to 0. And the other term that we have is s double prime minus 2js prime sigma z minus 2j alpha beta s plus beta squared minus sigma squared times s plus 2 kappa beta r equals 0. All right, so these two equations now, these are the coupled wave equations, right? Notice they're coupled in the sense that here we have the reconstruction beam, R, and S in the same differential equation. And similarly here we have S appearing, and we have R in the same equation. Notice, too, that R is coupled to S through the coupling coefficient, which appears in both of those equations. And S is coupled to R, again, through that coupling coefficient. So if these, our coupling coefficient were 0, we would just have kind of a normal propagation, wave propagation. But because we have that grading, which has in it the modulations, we end up with connecting to the other field that we said that was involved in the overall field. You see that? That's a very subtle point, but again, that's kind of at the crux of what's going on here. This coupling notion of coupling between these two fields. Okay, so now we have some coupled wave equations, but they're second-order wave equations, and let's see if we can trim that down a little bit and make it easier to solve. Did you have a question?
Second equation, you've got a term of beta squared minus sigma squared s.
Oh, this one?
Yeah. And
Yeah, what does that look like?
just above, you've got beta equals sigma squared. So is that not 0?
Yeah. So this is correct. This appears in this one where we're just coupling to the S field, the reconstruction field coupling to the S. But here when S is coupled to R, S also has this term in it because that represents the tuning parameter, right?
Okay.
You see, so the tuning nature is now directly falls into play. That definition that I brought out earlier was, not some arbitrary definition. It was a consequence of how it plays out these equations. Okay. So we I introduced it first, so it, to give you the physical aspects of it. But here we see the definition is actually quite natural from the coupled wave equations. All right. So let's see if we can make this set of equations a little bit simpler. Yeah.
Going on that same point, I still don't understand then the definition and then that term that's in there. So is that effectively 0 right now? Or are we saying there's no detuning between it?
Oh, well, okay. So if we brought these terms over onto that side, right, then we have the R's coupled to S's and the S's coupled to R's, right? It's equal to 0 in a sense, but I should really, we could, make this equal to minus 2 kappa beta S, right? And then the R's, you can see that directly related to this through that coupling coefficient. Okay. It's just, maybe I should have written that. Later I will. I'll make that distinction more clear very shortly. Yes?
I think it's really just the third term in the second equation. Why is beta squared minus sigma squared not equal to 0 when right above the box you said beta squared equals sigma squared?
Which term? This third term? This one? Or the fourth term?
Yeah.
Oh, because sigma, this would be 0 if we're at the Bragg condition. Okay? So that's again the meaning of that term. So in that very special case where we're at the Bragg condition, then this term would be 0. Okay? Yeah, thanks for bringing that up because that's going to come out later too. So. All right, so let's try making this a little bit simpler. So we said that there's no abrupt boundaries. And so what that means is that again, this interchange in power that we have between R and S is going to be very small, okay, and that kind of indicates that R prime and S prime are small. All right, and if R prime, so I mean they're not going to be 0 in our case, but if the first derivatives are 0, in this physical sense, the R prime and S double prime are going to be even smaller. Okay, so we're going to have, in the sense that we have R double prime is going to be much less than this rho sub z times R prime term, and similarly S double prime is much less than sigma z times S prime. Okay, And so what that does for us is allow us to eliminate these second derivatives. By not having this abrupt boundary, basically we can eliminate the second order derivatives in this field term. Later we'll briefly go through the rigorous analysis and we keep those second order derivatives, and we have to solve this equation in a very different way, a much more complicated way, but it's still possible, but the result is much less intuitive than what we're going to end up with. So when we make this assumption, all right, so again about this no abrupt boundaries, we can now make these coupled wave equations even simpler. And so if we define, let's define a couple of terms here. So define, as Kogelnik does, C sub r is equal to the z component of the reconstruction beam normalized to beta. And this is just equal to the cosine of theta, the angle of incidence, which is also an obliquity factor. We kind of talked about that earlier in the Fourier analysis. Here it's going to have a little bit different meaning in the sense that if we have a surface coming in at an angle here, we're talking about the component along the that interface. All right, so that's what this obliquity factor refers to. And similarly, we can define C sub s is equal to sigma sub z over beta. Now, sigma is defined, as we said, in terms of rho and k, all right? And so this C sub s is equal to cosine of theta minus k over beta times cosine of phi, all right? So if we use these, all right, we can then write the coupled wave equations as C sub r, r prime, plus alpha r equals minus j kappa s, and C sub s, s prime, plus alpha plus j times our detuning parameter. So we actually normalize that to 2 beta times s equals minus j kappa r. So here I wrote it not equaling 0. Okay, I just rewrote it a little bit, made it equal to the term that the other field component is coupled to. Okay, so these are some very simple coupled wave equations, and let's look at this now a little bit. So again, so this detuning parameter that we have here is equal to beta squared minus sigma squared over 2 beta. And again, so this represents sigma can be 0, or this detuning parameter can be 0, right? And it's 0 actually when, in fact, we're at the Bragg condition. So this equals 0 at the Bragg condition. And notice what happens if that term is 0, then this term in here is 0, which means there's less coupling back to itself. So there's a lot of coupling now between S and R. If this term is large, so if this current term keeps growing here, right, if we have, we're detuned way far from Bragg, then this term is much greater than that term, and we have very little coupling between S and R. Okay? The same can be said for alpha. If we have a lot of absorption, a great deal of absorption in this, then this term is going to be much larger than that. And so there's going to be very little coupling between that signal beam and the reconstruction beam. All right? So you can kind of start getting a feel for the sense of coupling and factors that are going to affect it. All right? So I think that's really one of the the really nice things about this particular formalism is that it gives us a kind of an intuitive way of thinking about the coupling and ways of estimating how strong degradings are going to, in sense of diffraction efficiency, are going to be. Now, we still haven't solved the problem, right? We need to find S really, or R. We can get S from R, but it's we could also get it in a straightforward way. All right, so we're almost there. We have a set of differential equations, first-order differential equations, and so we know how to solve these, right? We actually know what the solution is, right? So for a first-order differential equation, we know that the solution, when we have two of them, right, we know the solution is going to be this, right? For R of z, it's going to be equal to a constant, e to the gamma 1z, right? It's an exponential. And we have plus R2 e to the gamma 2z, right? From our Diffie-Hughes classes years ago, we know that that is the solution to a first-order differential equation. And similarly, S of z is equal to S1 e to the gamma 1 z plus S2 e to the gamma 2z. Okay? Now, S1, S2, R1, and R2, as well as gamma 1 and gamma 2, these are all constants. We don't know what they are yet, but we can find them, right? All right, so these are the solutions, right? So if we take these solutions and then substitute them into our differential equations, all right, we then end up with a set of equations in terms of the constants, all right? So we end up with now, so after substituting, we end up with the following. We have C sub r, gamma I. Gamma I means I is equal to 1 or 2, because we have two of them, plus alpha, and this is times r sub I, equals minus j kappa little s sub I. And for the second equation, we have C sub s gamma I plus alpha plus j times the detuning parameter, all times s sub I, equals minus j kappa r sub I. Okay? So again, we need to determine these constants. We don't know what they are. And so let's do the following. Let's multiply these two equations together, and we end up with a quadratic for gamma I. Okay? And this will help us, and then we can eliminate Ri and Si. So with that, we end up with the following. We have C sub r gamma I plus alpha times C sub s gamma I plus alpha plus j times that detuning parameter is equal to minus kappa squared. Kappa we know, right? Alpha we know, and the detuning term we could also get from the conditions that we're operating under. So this is the quadratic, and then we just solve that quadratic, right? B squared minus 4ac over 2a plus or minus and so forth. So we end up with two solutions. Gamma 1 and 2 now is equal to minus 1/2 alpha over C sub r plus alpha over c sub s plus j times the tuning parameter over c sub s. And here's the, I guess this is, and here's the plus or minus, so we have plus or minus 1/2 times alpha over c sub r minus alpha over c sub s minus j, the tuning parameter over c sub s squared, minus 4 kappa squared over c sub r c sub s, and we have to take the square root of that. Okay? And so the plus, now this refers to the gamma 1 and the minus here to the gamma 2. All right, so they're kind of messy, right? I mean they're algebraic expressions, but we know all the terms, right? We know all of those parameters. We know alpha, we know the tuning parameter, we know the coupling coefficient, right? Those are just terms that we know. So what we don't know are these yet, okay? And we need those in order to construct R and S. So we have the gammas, we have the exponential constants, but not the coefficients out in front of those exponential constants. So how do we get those? Okay, well, like our differential equation books tell us, we need the boundary conditions, right? So we need to utilize something else about the system. All right? Now, the boundary conditions that we have, so this is another assumption which is made. So we're making lots of assumptions as we go through this trail. So we're going to have to make some assumptions about the boundary conditions. All right, because of the nature of choosing this problem in a sense of no hard boundaries and only keeping these two waves. So the assumptions that we have to make are that we have, by looking at the situation, a priori, we say it's a transmission grating or we have a reflection grating. Okay. Now, sometimes this is easy, right? If we have an unslanted transmission grating, again, the notion of transmission grating is the beam propagates through. So this is easily identified as transmission grating. This one is easily identified as a reflection grating. Right? But what if we had the fringes at 45 degrees? Okay, so there are some ambiguities in this coupled wave approach. So 45 degrees, our solution is going to start, not being very accurate because we're going to have, situation that has, we can't really distinguish it between a transmission and reflection grating. We're probably going to get some, some diffraction coming in, in transmission and also some in reflection if we illuminate that grating with a very high slant angle. Okay, but we could just choose, let's say it's a transmission grating, and go that way, or we can say and then maybe if you want, you can say, okay, let's evaluate it if we assume then that it's a reflection grating. Okay, now the reason we do this is, again, we have to come up with some boundary conditions for the transmission and reflection grating. So let's first look at the transmission hologram. All right, and so here, again, we have something that looks like this. And we have the grating defined from z equals 0 to z equals d. And let's draw another figure or graph below that here. the same, this is a function of z in both of these cases here. And so when we illuminate this transmission grating, all right, we start out with a value for r. So we'll draw kind of the magnitude of the fields here. So we start out with some value of r, say a normalized value of 1 unit magnitude. So we have r of z here. And then as it propagates, that r is going to decrease, right? So at the end here, we'll have maybe a diminished r of z, and then we're also going to have hopefully we'll have some signal beam as well. Okay, so the signal beam starts out with a value of 0, right? There's no magnitude here, and then presumably it will grow somewhat to some value s of z at the output at z equals d. All right, and so in this case, both of these waves are traveling in the same direction. Okay, and so we can define the boundary conditions. We don't know. So the boundary conditions are: we don't know anything about what happens at z equals d, but we do know what happens at z equals 0. We have a value of r of 1. We have a value of s of 0. Okay. Now, what about for the reflection hologram? All right. So again, this is very different. So here's our grating again from z equals 0 to z equals d, and draw another graph underneath here. Z equals 0, z equals d. So what happens in this case? All right. Well, so again, so we come in here with r of z, but now the diffracted field is going to be coming back here, back into our incident space, and we could have some value r of z out here, okay, which is, say, a diminished version of this one. All right, so our r now is going to deplete as we go through. Start out with value of 1, and we have some other value r of z on the back face here, and it's moving in that direction to the right. But the s now has a value of 0 on the back face at z equals d and grows towards the front face, and it's moving in the opposite direction. Okay, so here we have this c sub s for the signal wave. This is a negative direction, so we end up with this cosine angle being negative, and here we have that c sub s is positive. So that's a kind of a difference between these two boundary conditions that we have. Okay, so we have the boundary conditions, so let's use them and come up with a solution, again, that'll give us these values here that we need. All right, so again, we're looking for R1, R2, S1, and S2. All right, so let's do this for the transmission case. All right, and so we said that R of 0 for the transmission hologram is equal to 1, and S of 0 is equal to 0. Right? There's no transmission diffraction efficiency at the start of the grating at the z equals 0. So this also is so we have this equation here, right? So z is equal to 0, and so these two terms drop out, and so r of 0 is just equal to R1 plus R2. Okay, so this is at z equals 0. And we also have S of 0 is equal to 0, and that's equal to S1 plus S2, because these values of z are 0 in that exponential as well. All right? So that's what we have to work with. All right, and so we can take our equations that we had. So we had that C sub s gamma I plus alpha plus j times this detuning parameter times Si is equal to minus j kappa Ri. And we have that, again, S1 is equal to minus S2 from this being equal to 0. All right. So with that, we end up with S1 is equal to minus S2 is equal to minus j kappa over C sub s gamma 1 minus gamma 2. All right. So the way we got that, right, is so the way we got that is by taking our value. So we put in S1 and R1 and S2 and R2. All right, and we can write this equation here as minus j kappa R1 plus R2 is equal to S1 times C sub s gamma 1 plus alpha minus j times the detuning parameter plus S2 C sub s gamma 2 plus alpha plus j times the detuning, and there should be a plus here, times the detuning parameter. All right. So this here is equal to 1. All right. So that's why we got rid of that over there. And here we have this then is equal to S1 C sub s gamma 1 plus S2 C sub s gamma 2 plus alpha plus j times the detuning parameter times S1 plus S2, and this term is equal to 0. All right. And then so again, using this, we end up with this minus sign here between the two gammas. So just in case you're interested where, how we got to that point. Okay, so we now have a value for S1 and S2, right? That's what we needed, right? And so now S of D, okay, and this again is evaluated, so this is evaluated at Z equals D. We have that S of D is equal to S1 e to the gamma 1d plus S2 e to the gamma 2d. All right? So all these terms are known, right? Gamma, although the two gammas that we had, although they're a little messy, are all in terms of parameters that we can evaluate, right? Those are all parameters for the grading, the absorption, the detuning, the coupling coefficient. All of those things are things that we know. D, of course, we know. And the efficiency, eta, is going to be proportional to this D, or S of D squared, okay? And so we pretty much have what we need there, all right? And so when we substitute in, for our S1 and S2, we have that S of D is equal to J times kappa over C sub s gamma 1 minus gamma 2 times e to the gamma 2d minus e to the gamma 1d. Okay, so that's what we were after, all right? And it's pretty general in many respects. I mean, it's for a transmission grading at least, if we assume that we do have that transmission grading, we can be off Bragg in this relation. Remember, gamma has in it the detuning parameter, or we can be at Bragg. We can have various thicknesses and different coupling coefficients that are either phase or absorption or absorbing in nature. All right. So, so that's S. I mean, we could also find R. All right. So, for R, if we wanted to find, R of D, here we know that 1 is equal to R1 plus R2. And so we can say R2 is equal to 1 minus R1, no surprise there. But R2 is equal to, again, using that same equation that we started with somewhere here. This equation here, we have that R2 is equal to J times kappa minus S2 over C sub R gamma 2 plus alpha, and we have, this is equal to J kappa over C sub R gamma 2 plus alpha times J times kappa over C sub S gamma 1 minus gamma 2, subbing in for this minus S2. All right? And so multiplying that out, we end up with that's being equal now to minus kappa squared over C sub R gamma 2 plus alpha times gamma 1 minus gamma 2 times C sub S. All right? And so so that's, we have R2, and so we have R1, and we can reconstruct R Z equals D, then is just, R1 e to the gamma 1D plus, I won't write it all out, again, R2 e to the gamma 2D, okay? So again, and many times, when you're working with holograms, like you're doing a lot of measurements, you may actually want to know, what that transmitted beam intensity is, because as you, say, are rotating your hologram to measure the diffraction efficiency versus angle, which you could then use to determine the diffraction efficiency versus wavelength, the diffracted beam may start to move a bit, okay? Whereas if you set it up so you're just measuring R, the transmitted beam, you can then, and that, R plus S equals whatever went into it, you can then calculate what the diffracted beam is from that. All right, so oftentimes you want to know what R is as well for experimental reasons. Okay, so next time we'll do the the solution for the reflection boundary conditions, and then look at some specific examples of different types of holograms, phase, absorption, and mixed holograms, both for transmission and reflection. Okay, have a good weekend, and we'll see you on Tuesday.